Every single time you search for something online, buy something, or stream a show, you're using a piece of tech that's doing some serious thinking in the background. Today, we're going to lift the hood on the relational database and discover that it's not just a storage closet. It's actually a really powerful computational engine.
Most of us, we kind of picture databases as these giant digital filing cabinets, right? Just these simple, passive places where we stash away unbelievable amounts of data. I mean, think about every single course, every student, and every instructor at a university. We put data in, we get data out. Seems pretty straightforward.
So when we ask it a simple question using a language called SQL, something like, hey, find me the names of all the instructors in the history department, we kind of expect a simple, quick answer to pop right out. But wait a second. How does the machine actually do that? How does it find that one tiny needle in a digital haystack that could have billions of records and do it, like, instantly? Well, the secret isn't just about clever storage. It's all about a powerful computational process that's happening completely behind the scenes. Okay, so to really understand that process, we need to get one crucial idea down first: the huge difference between telling a system what you want versus telling it exactly how to go and get it. So SQL is what we call a declarative language. You just specify what data you need, not the steps on how to retrieve it. It's exactly like ordering food at a restaurant, right? You just say, I'd like the lasagna. You don't go into the kitchen and hand the chef a detailed step-by-step recipe. A procedural language, well, that is the recipe. And yeah, this slide just breaks that down perfectly. The SQL that you write is based on this declarative idea called relational calculus. That's the what. But underneath it all, the database is this amazing translator. It takes your request and turns it into a procedural plan, that step-by-step recipe, using its own internal language called relational algebra. And that's the how. So what's in this how toolkit? What exactly is this internal language, this relational algebra? Honestly, the best way to think about it is like a set of fundamental building blocks for data, kind of like Lego bricks. The first, most basic Lego brick is called select, and its job is super simple. It just filters the rows. It looks through a table and pulls out only the ones that match whatever condition you give it, like, say, finding all the instructors who work in the physics department. So if the select tool is picking out the rows for us, our next tool, project, picks the columns. This lets you zero in on just the specific bits of information you actually care about, like grabbing only the names and salaries from that instructor table and just leaving all the other stuff behind.
But the real magic, the real power, comes from our third tool, join. This is the operation that lets us connect the dots between completely different tables. With a join, we can combine that instructor table with the course table to see exactly which courses each professor teaches. It creates a brand new unified picture from scattered pieces. And this is where the computation part really kicks into high gear. The wild thing is that these simple building blocks, select, project, and join, can be put together in a whole bunch of different ways to get the exact same answer. The absolute key thing to understand here is that there's never just one single path to the answer. For any question you ask, the database has multiple ways it could snap those Lego bricks together. It has choices. And you know what? The choice it makes changes absolutely everything. Let's make this real. Imagine you need to find the history instructors and what courses they teach. Okay, the database could take path one. Join the entire massive instructor table with the entire massive courses table, creating this gigantic temporary monster result, and then filter it down to just the history department. Or it could take path two. Filter the instructor table first, right? Find that handful of history professors, and then join that tiny little group with the courses table. Both paths get you the same answer, but the performance difference, it's not small. Path 2 could be thousands, even millions of times faster. And that right there is the database's core genius. Before it even touches a single piece of data, a part of it called the query optimizer analyzes all the possible paths. It uses its own internal stats to guess the cost of each path, and then it commits to the absolute cheapest, most efficient one. This is the computational heart of the database. So, all this clever internal computation, what does it actually mean for us, for the people building and using software? Well, it all comes down to one of the most powerful ideas in all of computer science: abstraction. This level of abstraction is, frankly, a total game changer. It means developers don't have to be these deep experts in the ridiculously complex art of query optimization.
They can just focus on declaring what data they need and then trust the database's computational engine to figure out the best possible how. This separation is what's made it possible to build the incredible applications that run our world. From our banks to our social media, it's the reason this model has been on top for almost half a century. So this computational model, this ability to separate the what from the what and always find the fastest path to the answer, it's been one of the most successful ideas in the history of computing. It's reigned supreme for decades. Which, of course, leaves us with a pretty fascinating question to think about. What's the next big computational idea that's going to define the next era of data?